Okay, so first of all, what is reasoning? At a very high level, reasoning is simply the intermediate tokens that you generate before you generate a response. So there is no very strict definition of reasoning. Let's say if you're solving a math problem, anyway, most of the time you cannot immediately arrive at the solution. If I ask you to solve a quadratic equation, you will require to generate the intermediate steps, right? So so those intermediate steps that you need to generate before you reach the final solution to a quadratic equation, that can be called as reasoning, or that can be called as chain of thought. So I will use these two terms, chain of thought and reasoning, sort of interchangeably. And now for maths, it's clear, right? For maths, you will anyway be generating those chain of thoughts. There's nothing you can do. In most cases, I mean, sometimes you can immediately arrive at the answer, like 2 plus 2 is always 4. So if I have to write it mathematically, I would say, let's say if pi theta is your language model and y is your final answer and x is your question, I will use this question, instruction, query sometimes interchangeably. So your reasoning is something I will denote by z. It's a it's an intermediate step that you need to reach y. So your network will first take x, generate z, the intermediate steps, and then generate the final response y, right? And if I have to write the distribution, I will write it like this: pi theta z given x times pi theta y given z comma x. This is your distribution of the reasoning or thought, and this is your distribution of the response given the reasoning and thought. Okay. So it can be something as simple as the steps that reach to a solution, but if you have a more complicated problem, where looking at the problem, it's not obvious what the steps can be. To an LLM, let's say it's not obvious what the steps. So ideally, what would you want? You would want that it should try one way approach, find if it does not go, if it does not solve the problem, then consider other approaches, consider multiple solutions, probably verify the answer also if it can, right? So you would want that the LLM should be able to do a bunch of other things while arriving at the solution for complex math problem, right? So that is a more complex form of reasoning, which the current generation of most powerful LLMs that are there, whether it's DeepSeek, R1 models, the Qwen 3 models, or the Grok 4 models, all the recent language models are trying to incorporate that reasoning in their modeling, right? Okay, so this is the format that we'll follow. We'll start. I mean, since most of you are already aware of what chain of thought is, we will just do a quick recap of this thing. Only a quick recap. And so the chain of thought is used only during inference time, right? You either tell the model that let's think step by step, or you give some chain of thought examples in the context window, right? So that the model can generate chain of thought for the response. So we'll look at those inference time approaches, and then we'll see what to do how to incorporate, how to actually make the model better at not only generating those chain of thoughts, but generating the response given those chain of thought. So can the model learn better thoughts? And when I say better thoughts, I mean that can it generate thoughts that such that the resultant solutions have higher accuracy. So we'll look. So there are these three approaches which try to train the model to generate better thoughts. The first one is quite simple. It just uses supervised tuning on self-generated thoughts. We'll discuss it in more detail. The second one again works with self-generated thoughts, and instead of supervised fine-tuning SFT, it uses DPO, preference optimization. And the last one, which is what revolutionized Reasoning is a DeepSeek R1 work, which uses reinforcement learning or online reinforcement learning, and specifically it uses GRPO, which is a type of online reinforcement learning algorithm with verifiable reward to improve the performance of the models drastically on a huge range of, I mean, they focused mostly on coding and math, but the later works showed that you can, using the approach that they provided, if you scale it further, you can improve the performance on a wide variety of tasks, not just math and coding. And we will talk about that in the later slides. Oops. Okay, so we'll start with a brief recap of what chain of thought prompting is, which I am guessing everybody is already aware of. Is or maybe if, I mean, is everybody aware of what chain of thought is? I'm hoping. Okay, all right. So let's do a recap of it. So there are two variants here. The that I will talk about. The first one is, so basically chain of thought is, again, right now think it's just the sequence of steps in a math problem, let's say, before you can generate the final solution. So if the question here is Roger has 5 tennis balls, he buys 2 more, each cans, each can has 3. What is the total number of tennis balls? You can either generate the solution immediately, 5 plus 3 into 2 is equal to 11, or what you can do is you can generate this intermediate step here, which, so the idea of intermediate step is that maybe you have a bias towards a certain solution. Maybe you like the number 12 and you said 12 at that point, but if you write each step of your thinking one by one, then you will quickly identify where the error in your thinking is, and then the chance of that error occurring reduces. So here what in this case we give a few examples in the context window. So in the prompt we include examples, and each of the example includes a chain of thought before it generates the final solution, right? So when we ask the question here, the model knows that it has to first generate a chain of thought and then the solution. So this is your this was one of the first ways to incorporate chain of thought reasoning in the earliest LLMs, I mean GPT-3. So after that, people thought that, do we need to provide this chain of thought, these examples in the chain of thought in the prompt to be able to generate chain of thought? And then there was this next paper. Oh, sorry. Yeah, so these are in context examples with intermediate steps, right? So the paper, let's think step by step. What they showed is that you don't need to provide these examples with the explicit chain of thought. All you need to do is add this prompt, let's think step by step, that give the question and just add this prompt, let's think step by step. And if you do that, the model automatically starts generating its thought process before it generates the final solution, right? And here, so this is the thought process of the model. And then finally you can, so this is a thought process, and given the thought process you can extract the answer. So you can you might give some instruction to the model that the last, you can say that the last word that you generate should be the answer. So you need some way of extracting the answer from the generated response, right? So you can give some formatting instructions to the model for generating the solution, right? You can common one that we use nowadays is that the final answer should be within boxed, like this. Put the final answer within boxed. We do this so that whatever is inside the box we can extract and then check whether the response was correct or not, right? So this is zero shot chain of thought prompting, where you don't need to provide the multiple examples with chain of thoughts. Okay, so these two are inference time methods, and if it works, it works. If it doesn't work, what to do then? I mean, if let's say I gave asked the model to generate a chain of thought, it generated some chain of thought, but the final response was wrong. Now, can I improve the model? How do I make the model better at generating thoughts? And when I say better at generating thoughts, I mean that the final solution accuracy should also improve, right? Not only the thoughts should look good or something, but the accuracy of the final answer should also improve. So if I ask you that, okay, I want to train a model that generates better thoughts and better solutions, better responses, how would you go about it, right? I mean, the immediate idea that will come to mind is, let me collect a data set first, right? Let me create a data set somehow, or collect a data set somehow of question, thought, and the final solution. And once I have that data, I can do training on top of it. I can maximize the log probability of thought given the question. I can maximize the log probability of answer given the thought and question. Those two things I can train, and then the model will become better at generating thoughts. But where do we get this thought data from? We can use human annotation. Some people have used human annotation in the past, but it's very expensive for a human to write thought for every answer and then the solution. It's probably not something that you want to spend money on. So so the other option is that let's try to use thoughts which are generated by the model itself. So let's try to prompt the model to generate thought, and then we can use those thoughts that result in correct solution. If we are working with a math problem, we can say, if the final solution is correct, I will try to use those thoughts for training. So that's what star tries to do, that it generates thoughts and then tries to use if the final solution is correct, tries to use those thoughts for training. You can also do something like DPO, where you generate multiple thoughts and pick the one that is the highest reward, pick the one that has the lowest reward, and make a preference pair out of them. So we'll look at that also, which is your TPO work. And the DeepSeek R10 effort is basically you generate multiple thoughts and responses, solutions, or whatever responses, and then verify the correctness of the final solution, use that as a reward, and then do reinforcement learning. That's what DeepSeek R10 did. Finally, if you don't want to use self-generated, you can, let's say you already have a powerful teacher model, then you can generate those thoughts from the teacher and just use that for training. That's I mean, basically, then you already have you can easily create a data set of this question, thought, answer, right? And you can do distillation. Okay, so let's look at the SFT approach, which is the star approach. So what it does is, it takes some few short examples with chain of thought that we saw earlier in the chain of thought prompting first slide. We saw a few short examples with chain of thought, and then it takes, this is your question that you care about, this is the question whose answer you want. And so here it is, what can be used to carry a small dog? Swimming pool, basket, dog show, backyard, own home. You feed it to a language model and it generates. Okay, so in the prompt, in the few short examples, you have output of the form thought, solution, thought, solution, thought, right? So so when you generate the answer, you will also have some thought and then solution. Let's say thought might look like, because we are talking about a dog and the dog is not very big, so maybe a basket can be used for carrying the dog. So that's what the thought will look like, and the solution would be B, basket. So you generate multiple thought solution, and then you extract the final solution that is there. In this case, the basket, let's say, or let's say if it is a wrong response, can be backyard also. And you also have the ground truth available, that what is the correct solution, and you just verify which of them matches the ground truth. And let's say the thought 1 and thought n match the ground truth. So now you can use these for creating your supervised training data. So now your data may look like, let's call this as x. So x, thought 1 and solution 1, this might be one training data, and x, thought 2, thought n, solution n. This can be another training data, and you collect your training data in this form, and now you can do supervised training on top of this data. Yeah, so this is a very straightforward approach of constructing your training data, and then you can do supervised training. Now, anybody sees a problem with this approach, that if we just construct our data this way, what might happen? Any idea?
Is there so much subjectivity in objective problem, like the element itself can Like if it all depends on what the LLM prefers, right? The data set.
Right. I mean, that is true. I mean, these are all self-generated approaches. So all the approaches that you see, the output will always be generated by LLM. Now, it might be the case, you're right, that the LLM may not even know the answer to this problem. All the solutions are wrong. What do you do in that case? In that case, basically, you have to discard this data. And another issue is that this is multiple choice. So just by random chance, even if the thought is completely wrong, you might end up with a correct solution, and you might end up training with a wrong thought. So with multiple choice, this problem is there. Then nowadays we don't use multiple choice. We mostly use maths problems or code problems where the final thing can be verified, not a multiple choice situation. Yeah, so both the issues are there. Okay, so now the issue is here is that we're training the model only on examples on which the model already knows the answer. So it might happen that out of 10 generated solutions, only one is correct, but the model at least knows the answer, right? So if the model fails to solve new problems, the training will saturate. Basically, you're not providing any signal, right? If there is, let's say, so all we can do here is that earlier 1 out of 10 was correct. Now maybe 10 out of 10 will be correct, but we're not solving any new problem that the model doesn't already know. So how do you train the model? How do you make sure that cases where none of the solutions are correct also get incorporated? So the idea that this paper used, the star paper used, was to give a hint what the correct solution is, and we'll see how the hint is provided. And it hoped that the model will somehow take the hint and it will be able to reason backwards why that answer is correct, and as a result, its rationale will become correct. So this is self-taught reasoner with the hint added. So you can see the hint here. Uh, Here we have just the hint. Basically, hint is just a word saying correct added to the correct solution. So it's not basically a hint. It's actually telling the model that something is already correct. And now you do the exact same thing that you would have done otherwise, which is do a forward pass to the LLM, generate multiple thoughts and solutions, extract the final answer, and verify the correctness, and then keep the ones that are correct, repeat, and then perform SFT. So it's exactly the same approach, but it's just that now you have added the hint as well. And another thing that I think I missed in the previous slide was you don't do it only once. You create this data set of correct triplets, do the training, then again generate the same triplets, and then do it. So you repeat this loop of creating data set and training again and again. And this is something that we will see in the next topic that I talk about, which is thought process optimization. Okay. Also, one more thing is that if at least one is correct, if at least one of the generated thought solution pair is correct, you don't apply a hint. One solution is correct, don't use hint. But if none of them are correct, then you can use hint. So this way they are hoping that the model does not overfit to the hint itself. If none are correct, use hint. Okay. So they tried it on some simple problems. This is one problem that I have taken, which is the n-digit summation problem. And the n-digit summation problem is that you give two n-digit numbers, let's say 179 plus 84. These are three-digit numbers. And now the model has task is it has to sum up these numbers, but it should also generate the steps that will reach the final answer. So the step would be, let's set the unit digit 9 plus 3, 12. 2 is the ones position, and it will write all this. 2 is the ones in the ones position, 1 is carryover. All those steps will be the reasoning. So now if you train the model without rationalization, and these are the number of SFT step number of as generation plus SFT iterations. So so you can see that one digit addition immediately jumps to 100% because that model already knows beforehand. Two digit addition, the performance climbs quickly uh, with now if you see, look at with and without rationalization. With rationalization the performance climbs much faster compared to without rationalization. So if we tell the model beforehand which of the solution is correct, it tends to learn much faster. That's what they observed, and this is true for across the digits 1 2 3 4 5. Okay, so now let's look at the second approach, which is the thought preference optimization. So this was the supervised tuning approach. Now let's move to preference optimization. So it will follow exactly the same setup. There will be two differences. One is that instead of a verifiable setup where you can exactly verify the solution, this will be a setup where you exact verification is not possible, like writing a poem, right? So you will have a judge. And the second thing is, instead of supervised tuning, we'll do DPO. That's the only two differences. Also, this paper decided to separate the thought part and response part in distinct chunks that we'll also see. So the idea is that if you these chain of thought approaches, they work well on math and logic. If you say let's think step by step, model's performance improves drastically on maths tasks. But if you look at the performance for text classification, and actually the performance drops for text classification. There is a drop in performance here. It looks like. So in many so maths and symbolic and logic, the performance improves. So these points are basically the points of the data set. How many of them for how many of them the performance improved, those will be in positive, and for how many of them the performance decreased, those will be in the negative. So these are the performance chain of thought reduces performance here, and for these cases chain of thought improves performance. So chain of thought does not help in all the situations. It does help in math and symbolic logic. And this circle that you see, you can see that this is also the jump in performance with and without chain of thought. So you can see that for maths it's much higher, whereas for other tasks it's almost zero, close to zero, right? For symbolic reasoning also there is some jump here. So other than maths and logic, can we do something more with chain of can we generate chain of thoughts that will help for other tasks also? That was the focus of this paper. In particular, can we do something for creative writing? Like if I want to write a poem, can I generate a thought first that will help me write a better poem, right? Similarly, if I am doing instruction following, can the thoughts help me understand what the user is trying to convey? So this is an example of a non-math, non-logic chain of thought. Write me a poem in the style of Neruda. So the thought process, so the output that you want, or the output that this paper wanted, is like this: that it should first have a thought. Here is my thought process: that okay, Neruda's style is known to being passionate and evocative. His poetry explores themes of love, politics, and then this is the final thing. So this part need not be shown to the user at all. In this case, this is just this can be thought of as a latent thought. This part can be kept hidden also, right? So the way, and people have explored latent method approaches, like variational approaches also for generating these thoughts, but this uses DPO. Let me show you. Oh, sorry. Yeah. So prompt the model. So what we want is that we want the model to always generate a thought first before the response, no matter what the task is. So the prompt looks something like this: that respond to the user query in a comprehensive and detailed way. Write down your thought process before responding, and write your thoughts after this. So you are giving the format that you want the thought and response to look like. You want the thought to come after, here's my thought process, and you want the response to come after, here's my response. So this is generic thought prompt, and they also experimented with specific thought prompt where you tell this must be exactly what the thought should also contain. So here they are telling that the thought should contain the draft response, its evaluation, and then you begin your final response. So in the first one, they are not telling what the thought should contain. The second one, they are telling that also to the model. So does it help if you add this prompt that asks the model to generate a thought first before the response for any task? So initially, if you just ask the model, what will happen is that the model has not seen this structure. Here is my thought process, then the thought. Here is my response, then the response. Especially for generating poems, right? It has never seen this structure in its training, or it may have seen very rarely this kind of structure. So the performance always drops in the beginning. You will see 2 to 3 percentage point drop. So initially, the responses are going to be worse with the thoughts than without the thoughts. So, but now you can do some training. You can train the model to learn thoughts that lead to better responses. So what they do is they use a judge model, a reward model basically, to judge the quality of the final response, not the thought part. And why not the thought part? Because thoughts, the judge models have never seen thoughts, so the judge models are not going to be good at judging what the thoughts are. They have seen only the final. They have trained only on the final outputs. So you show the final response, let's say the final poem that you get, to the judge, get and score whether the poem is good or not, and then use that signal to train your to actually use that signal to create your preference pairs, because they use DPO. You can also use non-DPO approach. You can use GRPO, PPO, whatever your favorite RL algorithm is. But these guys used iterative version of online DPO basically. So here they are rewarding the thought process based on the quality of the final response. If the final response, the final poem is good, they will say the thought is also good and give a reward of +1 to the thought. Or I mean, they are using DPO, so they will. I mean, basically they will use the thought also for training, corresponding thought. Okay. So this is a prompt: generate a thought followed by a response. Write a poem on a happy eagle. Okay, and this prompt you feed to your LLM, and I'm calling this LLM as pi theta t. Oh, so theta t and this t are the same. Unfortunately, the thought. But it's okay. I'll keep it like this only for now. T is the t here. Theta t is your LLM, or the parameters of the LLM after t iterations of training. So initially it will be theta 0, and then after each training you will have a different LLM from which you will sample. So you start with pi theta 0, and let's say you sampled a bunch of thoughts. Here is my thought 1. Here is my response 1. So you get a bunch of thoughts and response. So again, you can see the thought and response, everything is model generated here. Nothing is the ground. There is no ground truth in this case. Actually, we'll not even talk about ground truth here. We'll use a judge model instead of a ground truth. And so you extract the response part, because that's what will be fed to the judge model, and you feed all this responses to the reward model, and the reward model gives you a number, a score associated with each response, depending on how good that response is. So here, for example, if you are writing a poem, then the response will be actually a poem, and you will feed each of those poems to the judge model, and then you will see which your judge model or your reward model says as the best poem, and which the judge model says as the worst poem. So here, this is the highest reward, this is the lowest reward. Let me put this like this. So
what are the t-wire index in your bracket?
T is the thought. Yeah. So
we are generating the thought given the response and the input, right?
We are generating a thought and the response given the input, correct? Yeah. So now you'll pick this. So although you're getting reward for the response, you're not picking the response. You're picking this entire generation. Here is my thought 1. Here is my response 1. This is your chosen output, and this is your rejected output, which on which you will train. So we'll train on this entire thing. This entire thing. Here's my thought. Here's my response. and you collect these preference pairs for the entire data set of prompts, and you get a huge set of preference pairs for training. And then the next step is, so let's say xt plus y plus is the correct triplet, the chosen triplet of prompt, thought, and response, and xt minus y minus is the rejected triplet. So then you just do DPO. This is just this is not an explanation of how DPO works, because that is already covered, and just put a slide about. So you will take these triplets of chosen and rejected, you will feed to your LLM that you are training. This is the one that you are training, and this is the one that is fixed, theta t. You will take the LLM that is fixed, and you will compute a reward. This is the implicit, this is called the implicit DPO reward. Implicit DPO reward is the log probability ratio under the model, between the model that you're training and the model from which the sample actually came from, the model used for generating the sample and the model. So this is the model that generated the sample, right? So you take this log probability ratio of the thought and the response for the correct pair, or the correct thought and response, and similarly you do it for the rejected thought and response, and then you maximize the objective, DPO objective, which is simply log sigmoid beta times positive reward of positive, implicit reward of positive minus implicit reward of negative. So if you guys have forgotten DPO, maybe it will be a good time to go through the slide. So this is the full picture. You start with your query or instruction. You prepend this, the thing before responding, generate a thought before generating a response, and then give it to the LLM. The LLM generates multiple thought response pairs. You evaluate the response only using the judge, and then you, based on the reward, you pick the accepted thought response pair and the rejected thought response pair. You give it to the LLM for training, and then you again repeat this generation process, and you do it multiple times. And how many times can you do it? So let's see how many times. Okay, this is the length control part, which Professor Tanmay was referring, but it's not in the GRPO setting. This is in the DPO setting. So the issue is that if when you keep on doing this thing, the problem is that many of these judge models, they tend to prefer longer responses. They like coverage rather than precision. They like recall more than precision, many of these. So they want that the response should cover all aspects. And as a result, what happens is that your response length or your tends to grow with each iteration. So they use length control, the authors of this paper, while selecting the preference pairs. They define a normalization function, which is that given any set of rewards or values, not just reward, given any values, you just subtract the mean and divide by standard deviation, the standard normalization of the score. So you do it for rewards, and you do it for the length of the samples also, and then you combine the two. Your reward is the standard normalization of the reward minus rho, which is a scaling parameter. And what does this rho decide? Rho basically says that how much weight do you want to give to length. Maybe you want to not give any length. So generally this value is kept very small, somewhere between 0 to 0.04. So you don't want to give too much weight to length. If you give too much weight to length, what will happen is the model will, this is a very easy reward to overfit to, right? So whenever you give some model an easy reward to overfit to, that's what it will focus on. So it will just say that, okay, if you don't want like length, I will generate 0 length outputs. So you don't want to give a lot of weight to this. And now you can use this reward for creating the preference pairs instead of the earlier reward. Yeah. Okay. So you can use this new reward for creating preference pairs. And so they compared it to a direct response baseline, which is direct response means that directly do SFT on response part only. And they trained on the open assistant data set. I don't remember what the judge model was here. Yeah. And the performance compared to SFT is better, not by so the performance improved on. So these two are what should I say? More like uh, chat benchmarks, where you ask the model a question, general question, and also provide some instructions like the first letter should be begin with T or something, and the model generates and you generate the model generates an output, and then you evaluate it. So these are both of these Alpaca Eval and Arena Heart are chat benchmarks which are evaluated using either humans, in most cases using LLM as a judge, GPT-4 or something. And this is a performance improvement with training iterations. You can see that the performance for Alpaca Eval improves till 3 iteration, and then it starts dropping somewhat. Similarly, on Arena Hard, also the blue curve is basically your TPO curve, and the performance. Sorry, the blue curve is not the TPO. So the orange curve is the TPO curve, and initially the performance is lower than the direct baseline, and that's because the model has never seen thoughts during its training, and as a result, its responses are initially bad. But then it overtakes the SFT baseline. But after a while, it saturates. The performance does not keep improving. So why does this performance not keep improving? This is the category-wise breakdown. So the performance on creative writing compared to SFT, on creative writing, on game development, there is not a huge improvement in performance. On research and analysis, language translation, marketing and sales, there seems to be a huge improvement in performance. Math and calculations also. Not huge, but there's some the model is doing better than SFT to some extent. Not a very large difference, I would say. So what happens if we keep on training? Why does this performance saturate, and what happens if we keep on training? Any idea? So remember, we are using a reward model, and the reward model is trained on its own finite set of data, which has its own bias. And now if you keep on training using that reward model, what will happen is that the model will try to generate outputs which your reward model likes, right? Responsive which the reward model likes. So maybe reward model has learned some bias that it likes outputs that contain a specific word. And that's what happens a lot of many of these reward models carry these biases because they have a limited they're trained on limited data, and they have a limited set of parameters anyway, so they cannot capture all possible correct and wrong solutions. So reward hacking. So yeah, so reward models are not perfect. So what will happen is that your LLM, if you keep on training forever, it will learn to hack the reward model, and the average reward will still keep on improving, but your performance on benchmark will keep on decreasing. The other issue is that we are not changing the training data. We are always using the same set of prompts, generating the preference pair and training. So we'll overfit on this data also, right? And the last point is DPO approach picks only the generated and the preferred and rejected response. It throws away everything. I actually don't want to throw away everything. I want to use all the samples also, let's say. So what do I do? So let's, for the first one, reward models are not perfect. We have discussed this problem before of reward hacking. And one solution is, let's focus only on problems where you know that the reward model is going to be very good. The reward model is going to be exact. And that scenario is verifiable rewards. Also, the data set keeps getting harder. So if we can use a data set that keeps getting harder so that we don't overfit, that will also be good. We'll not talk about this. This is curriculum learning. Maybe in the next class we can briefly talk about it. And then we want an RL method that can use all the samples, which is GRPO, PPO, any of those methods that don't only create preference pairs but reward each of the output, right? So the next thing we'll talk about, we will not cover it today, is this GRPO, using GRPO for reasoning. Okay.